Hello, can you hear me?
Yes, sir.
Namaskar. I'm deeply honored to have been invited by the physics department of this August University BHU to give this colloquial talk on Bose and his statistics. Now, I had the great privilege to have discussed this matter personally with Professor Bose. And through that, I gained certain insights into his work, which is not usually available. Which is not, now it's better. I hope. Should I have to repeat again? As I was saying, I had the great privilege and honor to have personally known Professor Bose as my teacher, and he used to call me sometimes to just discuss, and used to tell me stories and so on. And thus I gained an insight into his mind and his work, which is usually not available publicly. Particularly, the way Bose Einstein statistics is taught in most universities across the world doesn't actually do justice to what he did, and which only the great Einstein could grasp and appreciate. The usual way of teaching Bose statistics does not take into account or does not actually reflect what he actually did. And let me try and show you something. And this I got, again I repeat, by talking to Professor Bose and reading his paper very, very carefully. Okay, so Professor Srirup Rai Chaudhuri has already told you about the Planck law, which you all know. Oh, sorry. Sorry. Where is the laser pointer? Oh, at the bottom. Okay. Okay. So this is the famous formula, and as you all know, the nu is the frequency of light that we are talking about. Actually, it's between nu and nu plus d nu, a small range. C is the velocity of light. H is Planck's constant, and this is the famous factor. Now, as you will see, this consists of two different factors. One is this factor, and this is the second factor. Now, in all earlier derivations of this Planck's law from theoretical concepts, by the way, Planck discovered this law by looking at the blackbody radiation spectrum, which had been plotted by experimental physicists before him. Now, it so happens that one of them, I think Warburg or somebody, was having tea with Planck sometime in December 1900. And he showed him all the curves. And after he left, in a short while, Planck wrote down this formula and saw that it fitted the curves exactly. But he had to introduce that constant h, which didn't exist in physics before him. So this is an empirical law. Having established the empirical law, which fits all the experimental curves, he had to somehow try and give a derivation of it from basic principles of physics. But he failed, because there's nothing in classical physics which has this constant H. However, accepting that such a constant exists in nature, he made some attempts to derive this law. And one of the assumptions he made, as Professor Raichaudhuri told you, is that this does not actually mean that light consists of photons. All it means is that the walls of the hologram in which this Planck radiation is contained, it emits, it absorbs and emits in these quanta. That is, the matter is quantized, not the light. So this is one thing that you should understand very carefully. Planck was very much against the concept of photons. And for a very, very long time, for about 20 years, he fought against Einstein's idea, as many other physicists did. It was only Einstein who kept on saying that, but something like that must be there. And many others gave derivations of this thing. But in all these derivations which preceded Bose, which started from Planck all the way up to Pauli, the first factor was always taken from classical physics, as if the radiation is classical. Then this is the number of modes of the electromagnetic radiation in unit volume. You must have all done this, or if you haven't, you'll soon do this in your class. So this is that factor. This is the quantum factor. And all people were trying to do is how to get that factor by assuming various things about how radiation interacts with matter, various models. Now, Bose was teaching quantum physics to his students in Dhaka in those days. And he found it very difficult to explain all this to his students, because in his own mind, he didn't really understand what was going on, because he said that this kind of deriving this from classical theory and that from quantum theory is hodgepodge. It's logically unsatisfactory. So he wanted to give a derivation of the whole formula from quantum physics alone. And he succeeded. And that's why his derivation is so different from everybody else's, and it also brought in this new counting. Now let's go forward. Okay, so Bose found this logically unsatisfactory, and he solved this problem by deriving the first factor. The second derivation of the second factor was done by others. Nobody derived the first factor from quantum theory. This is what Professor Bose did. And then the rest just followed by applying the known, as he said, the known methods of statistical mechanics. You automatically, the derivation of the first factor is the most important thing. So, Bose, in his famous letter of 4th June 1924 to Einstein, said, "You will see that I have tried to deduce this coefficient, 8 pi nu square over c cube, deduce this coefficient, deduce this coefficient independent of the classical electrodynamics. So how did he do it? What he did was exactly the same thing that Planck had done for material atoms. He did the same thing for photons. Because by 1924, the fact that photons exist was empirically compelling, particularly from the experiments of Compton. So there was hardly any empirical basis for thinking otherwise. So Bose said, okay, let's accept that there are photons. Then what happens? I can think of the phase space of a photon. Now you know phase space, I suppose. Everything in classical physics, we talk of phase space as the space of the three spatial dimensions and the three directions of momentum. So six dimensional. So if I want to calculate the phase space of a single photon of some momentum p, then it's the spatial volume times the volume of the momentum space. So if you integrate that, from here you just get the total volume. And from this factor, if you use spherical polar coordinates, then you can evaluate this as 4 pi p squared dp. And then he does something fantastic, which also Professor Shirupurachudi has hinted. He uses this relation P equal to h nu by c, which Einstein had used, which is basically de Broglie's relation but for a massless photon. Einstein had already used this. So he said, okay, let's use this formula. So for P, let us substitute h nu by c, then you get this. Now, since the irreducible regions of phase space are of size h cube, this is his argument. Again, this is something which Professor Rayachandran hinted at. So the irreducible elements are h cube. What does that mean? It's basically using Heisenberg's uncertainty principle, but in a very rudimentary, in a totally different way. So what he is saying is, this is my total volume. So if I divide by V, it will be per unit volume. And then if I divide by h cube, which is the elementary volume below which you cannot go, then what do you get? You get 4 pi mu squared d nu over c cube, not 8 pi. Have you understood this? But this is wrong by a factor of 2. So what happens? So this is where Bose's genius comes in. And he told me one day, and let me tell you the story. I had gone to see him in the afternoon. He was in great expansive mood. And he said, today I'll tell you something, but never ever reveal it to others. But today I'm revealing it to you, and I revealed it in writing in many places. I'll tell you why. He actually was very secretive. He got up, he closed all the windows and doors, and then he came and said to me, and started talking to me, saying, you see, if you look at my derivation, it's a 4 pi, not an 8 pi. So I thought about it and I said, if the photons have a spin, and they go, the spin is parallel to the direction of motion or anti-parallel to the direction of motion, I'll get this factor 2. So I wrote that down in the paper. But then he says, let me say this in Bengali to you and then I'll translate it. He said, Budo, hite dile. The old man crossed it out. And he replaced it by saying, oh no, this factor 2 comes from the two states of polarization. Then Professor Bose smiles at me in a wicked way. And he says, I can understand the polarization of a wave, but what is the polarization of a particle, tell me? So he was trying to get it from the concept of a particle. So what is the polarization of a particle? It doesn't make any sense at all. So, in the paper, which was translated from English into German by Einstein, the following statement appears. It seems, however, appropriate to multiply this number once again by 2 in order to take into account the fact of polarization. This is Einstein's insertion according to what he told me. Now, I have no other proof of it except for Professor Bose's statement, but not quite. I'll come to that later. There is some other evidence of it. However, in the paper, this is what is written. So, if you take this factor of 2 into account, then that 8 pi nu square comes, and then by using standard, then what he did is, oh yes, this is very important. Before him, people were using abstract ideas of some quanta floating around and so on. But here Bose brings in physical photons and sorry, I have sorry, I'm not used to this, so I'm going up and down. So what is now the meaning of this first factor? You remember that usually you are taught that this is the number of modes of vibration of electromagnetic waves. Now, after Bose's derivation, this factor acquires a completely different physical meaning. The meaning is, it is the number of elementary cells in the phase space of a photon. He's calculated the total phase space of the photon divided by HQ. What does it give you? The number of possible states. He told me one day, Baba, I was not counting photons, I was counting states. This is a very important point, extremely important point. So the number of photon states is 8 pi nu square d nu by c cube. That's it, basta, period. So now you distribute the photons in those states. Now in equilibrium, it will happen that some states will have no photons, some will have 1, some will have 2, some will have 3, etc., etc. If you add them up, it must give you the total number of photons. And that will also fix the total energy. Now, so each of those states is characterized by what? The number of photons in them. Okay? Some has 1, some 2, some 3, some 4, etc. Now if you take any state with 2 photons, if you permute the 2 photons, will you get a new state? No, because the number of states is fixed. Number will not change. And therefore, the concept of indistinguishability automatically arises. The way it is, Bose statistics is taught, is to say, oh, sorry. The way Bose statistics is usually taught, you are told that indistinguishability was just a assumption which at that time had no basis. Completely wrong. If you look at his paper, indistinguishability is deduced from this derivation of the first factor. The problem is this derivation of the first factor is never taught anywhere. And so once you take this first factor from classical theory, then of course indistinguishability will have to be imposed. Bose did not do that. So the number of photon states or the number of possible arrangements of a photon in unit volume, then once you have that, you can calculate the probability of that state, W. Once you have the W, you use the Boltzmann formula that the entropy is K log W. You maximize the entropy subject to the constraint that the total energy does not change, and you should get the distribution. And that's what Professor Bose did, and he got the entire Planck's formula in one go. Now, why was Einstein so happy, whereas others were skeptical? Everybody else was skeptical, including Schrödinger. When Einstein wrote his 3 papers following Bose's, there were a lot of criticisms from Ehrenfest, from Schrödinger, saying, no, this is the wrong way of counting. You can't count this way. So there was a lot of opposition. The reason that Einstein was delighted was the following, two critical reasons. One was that when he proposed his photons in 1905, he clearly said that these photons propagate independently, like independent particles. Immediately, people like Nathanson and others, Ehrenfest, they pointed out, but if that is the case, if you have Einstein photons propagating as independent particles, you can never derive Planck's law from it. It's inconsistent. And that was another reason why people didn't want to accept Einstein's idea of photons. Secondly, people said, we can see interference with light, but if light is particles, we shouldn't. So this young man, he's a brilliant young man, but on this count he's wrong. So when this came, and Einstein saw that the photons were not propagating independently, there were these mysterious correlations, the Bose correlations. Then he said, now I've got it. And he started pushing the thing forward, and he said, if it is applicable to photons, why shouldn't it be applicable to material atoms? And that's where Einstein's genius came in, and he extended Bose's method to material atoms, where he had to introduce an additional constant, which is called the chemical constant, mu. Okay, now what was the objection? The objection was, Ehrenfest's objection was the following. He said, now this, when you do statistical mechanics or just statistics, you deal with independent things. Now your photons are not independent of each other, there are correlations. You just can't do statistical mechanics. Full stop. That's wrong. And you know how Einstein replied? It was in his third paper. In the paper in which he deduced Bose Einstein Condensation, he says this. He says, Ehrenfest has raised this objection. My answer is the following. Brilliant. He says, this is the only counting method in which, as you go 10 towards absolute zero, everything condenses to a single state. So the number of steps is 1. And if I calculate the entropy, log of 1 is 0. So this is the only method of counting which is consistent with Nernst's heat theorem. That was Einstein's answer. And then Einstein said, I agree that there's some strange correlation. We will understand it later on. Because even today we have not understood it. That's a fact. It is the way, and that's why statistical mechanics itself had to be changed into quantum statistical mechanics. And then, of course, he deduced, as Professor Umakant Rapol has said, why a gas of Bose-like particles should condense to a single state, and that became known as Bose Einstein Condensates. The very idea of counting is Bose's, but this particular conclusion from it, the extension of Bose's idea to material atoms and then to condensates, is Einstein's. I think so, therefore the name is appropriate, Bose Einstein Condensates. Now let me finish by giving you something else. I told you that my teacher had asked me never to divulge this conversation with him to anybody else. And I am divulging it to you today. I'll tell you why. Just before celebrating S N Bose's centenary in the year 1994, he was born in 1894. I was in the S N Bose Center, and the director, Professor Chanchan Mazumdar, had asked me to do this work, to bring out 2 volumes of his works. So I was searching for all possible papers that he might have published here and there but were not recorded. And I was browsing through journals in the Indian Association for Cultivation of Science. And I was looking at old volumes of the Indian Journal of Physics. And I suddenly saw one paper with the title, Experimental Proof of the Spin of the Photon, and by none other than C.V. Raman and S. Bhagavanthan. So I was intrigued and I looked at it. And you see what it says. In his well-known derivation of the Planck radiation formula from quantum statistics, Professor S N Bose obtained an expression for the number of cells in phase space occupied by the radiation and found himself obliged to multiply it by a numerical factor 2 in order to derive from it the correct number of possible arrangements of the quantum in unit volume. The paper, as published, did not contain a detailed discussion of the necessity for the introduction of this factor, But we understand from a personal communication by Professor Bose that he envisaged the possibility of the quantum possessing, besides energy h nu and momentum h nu by c, also an intrinsic angular momentum plus minus h by 2 pi around an axis parallel to the direction of its motion. The weight factor 2 thus arises from the possibility of the spin of the quantum being right-handed or left-handed, something we call helicity these days, corresponding to the two alternative signs of the angular momentum. There is a fundamental difference between this idea and the well-known result of classical electrodynamics, to which attention was drawn by Poynting and more fully developed by Abraham, that a beam of light may, in certain circumstances, possess angular momentum. Thus, according to the classical field theory, the angular momentum associated with the quantum of energy is not uniquely defined, while according to the view we are concerned with in the present paper, the photon has always an angular momentum having a definite numerical value of a Bohr unit with one or the other of the two possible signs. Okay, so after that, he says what he has done. They scattered light from molecules which could rotate. And if the photon has a spin, it can either deliver that unit to the rotating planet, either this way or that way. So, as you know, when you scatter, the main beam forward goes unchanged, but then there are two other spectral lines which you see, which you call the Stokes and anti-Stokes lines. And they deduce that if Bose's idea of the photon is correct, then the weight factors of the Stokes and anti-Stokes lines will change compared to the classical results. And that's exactly what they found. So this, by the way, is the first experimental demonstration in the world of photon spin. The Sahibs did it much, much later. And this is a beautiful paper. I showed it to my friend Girish Agarwal, and he was absolutely zapped. He said, this is just unbelievably beautiful. So see what these people were doing in the 1920s. And where are we today? So a shot prepared by an unknown physicist in an unknown university in a far-off British colony contained two new seminal ideas, actually three according to him. The idea of indistinguishability of photons. Actually, this follows from the fact that this HQ factor, these are interlinked. And the idea of an additional degree of freedom of the photon, which later came to be called spin. And as you know today, spin can be 0, half, 1, 2, etc. And then you have the division into fermions and bosons. And spin is something that you cannot get from phase-space considerations. It is something beyond space and momentum. That is why it's called an internal problem. Internal does not mean anything to do with psychological internal, but something which is not given in terms of the actual space, momentum, etc., which we are familiar with from classical physics, something beyond. So all internal symmetries then arose basically out of this idea. Thank you very much.
What mesmerizing lecture. We can take a couple of questions if any of you want to say anything.